And more specifically, the practice of Islam demanded that its followers have a very clear idea of the size and shape of the world.
Now this is crucial information for Muslims, because wherever they are in the world, they need to know the direction to Mecca for their prayer. This is known as Al-Qibla. Now, over such a large territory, finding the direction to Mecca is not a trivial problem.
This problem was wonderfully illustrated when a mosque was built recently in Washington, D.C. Some worshippers were confused because the direction they were told to face when praying was slightly north and not southeast as they expected. After all, Mecca is southeast of Washington, and on a flat map it does appear to lie in that direction.
But on a curved sphere, the shortest distance between any 2 points follows what's called a great circle. So for example, this great circle line between Washington and Mecca is quite different to what you might expect. So the direction to Mecca from Washington actually points slightly northeast rather than southeast. Of course, this is complicated stuff, but the key point for Islamic scholars is that knowing the direction to Mecca requires a knowledge of how steeply the earth curves. And that means knowing how big it is.
So Al-Ma'mun commissioned his very best scientists to measure it.
Hello.
Hello.
I'm Jim Al-Khalili. Nice to meet you.
To understand how they did it, I'm meeting up with Professor Sami Chaloubi from Aleppo University in Syria, who's an expert in early Islamic science.
Come and join me.
عندما قسمها على 7.5 عندما قسمها على 7.5.
Professor Chaloubi began by explaining the measuring technique, which Al-Ma'mun's scientists first used and which they had inherited from the Greeks.
We're now talking about the earlier
Yes.
Aristophanes technique of measuring the circumference. It was repeated again by the Abbasid astronomers, was to measure the distance between 2 points and then look at the angle of inclination of the sun. So in Egypt, in Aswan down in the south, they regard the sun as being vertical. This is near to the equator. And they worked out how far away from the vertical the sun was if they measured it from the north of Egypt in Alexandria, which is on the Mediterranean coast.
Al-Ma'mun's astronomers repeated the Greek experiment in Syria and Iraq by measuring the angle of the sun in the sky at noon at one known location. They then walked due north to a second location, carefully measuring the distance they travelled. At the second location, they once again measured the angle of the sun at noon. This angle would have been slightly smaller than the first one. With these figures, Al-Ma'mun's astronomers were able to estimate the Earth's circumference. They got a value of 24,000 miles, within 4% of the correct value. Not bad, you might think, but this method was flawed and ultimately unreliable. The main problem with it was that measuring the distance between two locations was incredibly difficult. It could only be done by the unreliable method of counting paces as you walked through the burning desert. A more reliable and sophisticated method for estimating the Earth's size was needed, and 2 centuries after Al-Ma'mun died, it came. What made it possible was a great leap of imagination, and the fact that by 900 AD, much of the world's mathematical knowledge had been translated into Arabic, so scholars could scrutinize and improve on it. Out of this obsession with scholarly learning came a true mathematical visionary, Abu Rayhan Muhammad ibn Ahmed al-Biruni. And like all Islamic scholars of the time, al-Biruni was obsessed with the science and mathematics of the ancient Greeks, Babylonians, and Indians. And because of the success of the translation movement, he had literally on his desk the great work on geometry by Euclid, Ptolemy's Almagest, the Indian text, the Sinhind, and the famous work on algebra by Al-Khwarizmi. Professor Chaloubi has brought along the book in which al-Biruni describes how he combined algebra and geometry with some very simple and practical measurements to solve the epic problem of how to calculate the size of the Earth.
بيروني ذي text مبرمون.
This is his
القانون المسعودي.
the Mas'udi canon.
Yes.
This is Biruni's canon, which I've been trying to get hold of, where he describes this fantastic experiment. And oh, you found the page.
Yes.
Having read al-Biruni's description of how to estimate the size of the world, I wanted to try it for myself.
First, he had to find a fairly high mountain from the top of which he could see a flat horizon. In this case, the sea.
What I love about this story is that with a few simple measurements around this small mountain peak, you can work out the size of the whole world. Al-Biruni's first step was to work out the height of the mountain. He did this by going to 2 points at sea level, a known distance apart, and then measuring the angles from these points to the mountain top.
So, to measure the angle to the mountaintop, Biruni had to use a device like this, called an astrolabe. It's basically a giant protractor. It has the angles and degrees marked around the outside, and a pointer to help him determine his line of sight. So if we try now and determine the angle to the top, it has to hang freely, and then, okay, so if you let it hang.
I'd like to stress, if you haven't noticed already, that al-Biruni would have made his measurements more meticulously than I am. He did them again and again to get consistently reliable results.
Okay, that's about it. And that is 24.5 degrees. Okay, so now we've determined one angle. We now have to go and pick our second spot along the beach.
The distance from the first to the second point must be measured accurately. In this case it's 100 meters, and the 2 points must be in a straight line with the mountain. I measured the second angle to be about 26.5 degrees, and now had enough information to calculate the height of the mountain. Using trigonometry and algebra, al-Biruni used a formula that relates the height of the mountain to what are known as the tangents of the angles he measured. Using my measurements, I get a figure for this mountain of about 530 meters. I now need only one more measurement to get the size of the Earth. And to get that, I have to climb to the top of the mountain.
What Biruni did next was measure the angle of the line of sight to the horizon as it dips below the horizontal. So we're going to try and reproduce that. So if you can lift it up so that it's hanging, and if I locate the horizon, okay, which is about 0.5 degree, which is about the value that Biruni got. Now here's the really ingenious part. Biruni had measured 4 quantities, 3 angles and a distance. He used 2 of the angles and the distance to work out the height of the mountain.
Al-Biruni now had everything he needed. In essence, al-Biruni imagined a huge right-angled triangle which has as its 3 corners the mountaintop, the horizon and the center of the Earth. Trigonometry told him that the angle he had measured and the height of the mountain are related to the radius of the Earth, and algebra allowed him to calculate it.
With this formula, Biruni is able to arrive at a value for the circumference of the Earth that's within 200 miles of the exact value we know it to be today, about 25,000 miles. That's to within an accuracy of less than 1%. A remarkable achievement for someone 1,000 years ago. For me, Biruni's experiment is an early dramatic example of a scientist using mathematical reasoning to extend humanity's reach. He really pushes the idea that abstract geometrical rules governing idealized shapes like perfect circles and triangles can help us to comprehend the real world.